Today we have the pleasure to have Professor Moussa Youdim. Professor Youdim is a professor emeritus of the Technion. He is the director of the Yves Toff and U.S. National Parkinson Foundation Center of Excellence, the Faculty of Medicine at the Technion. He's also a distinguished professor at the World Central University in Yonsei University in Seoul, in South Korea. He is also distinguished chair professor at Poly University and also at Hong Kong University. Professor Youdim received his BSc, MSc, and PhD in biochemistry at McGill University in Montreal, Canada. After graduation, he carried his research as a senior research associate at the University of London, later as a Wellcome Fellow at the Collège de France in Paris, and later as a member of the Faculty of Clinical Medicine at the University of Oxford in England. In 1977, we were lucky to have Professor Youdim moving and joining the Technion as a professor of pharmacology at the Faculty of Medicine at the Technion. Professor Youdim has done extensive research, and he's a world expert in Parkinson's and Alzheimer's disease, among others. He has published more than 800 scientific articles. He edited 45 books, or perhaps I'm not updated, more than that. He's on the editorial board of more than 40 international scientific journals. Professor Youdim is the inventor, together with Professor Finberg, of the Azilect. This is a drug marketed by Teva for Parkinson's disease. He's also the inventor of several other drugs, 4 or maybe more. Some are in preclinical tests. He has been named as inventor of more than 100 patents in neuropsychiatric and cardiovascular drug development. For his outstanding, remarkable scientific achievements, he has received numerous major awards and honors all over the world. So I was going to quote them, but then I found out that there are 2.5 pages of honors. So it will take part of this talk, so I give up. I will only tell you that these honors came from Israel, United States, England, Germany, Iran, Denmark, Holland, Switzerland, the whole list. So I'll just mention 3. In 2010, Professor Youdim was elected as a member of the Leopoldina German Academy of Science. He was nominated to the Hungarian Academy of Science. He received the European College of Neuropsychopharmacology Lifetime Award. And this was only 1 year in 2010. So I'm very glad that he agreed to come and talk to us about his work. Please.
Thank you very much, Moshe. I'm delighted to be here, but please forgive me if I have a relapse. I just came back from Florence at 5 in the morning and just giving the lecture on Parkinson and Alzheimer's disease. I have given this lecture in Korea to talented science students. In Korea, they have special schools for high school students who are really brilliant, and so the lecture I give you will not be very detailed, but what's happening in the field of Parkinson and Alzheimer's disease. And I'll try to keep it simple. And one of the major problems with brain diseases, namely Alzheimer's and Parkinson's disease, is that all of us in this room are losing our neurons at a rate of about 3 to 4% every decade. And if we live long enough, we lose a significant amount of neuron to either develop Parkinson's disease and Alzheimer's disease, because we know that Alzheimer's and Parkinson's disease lose their neurons much faster than normal people. And if you lose about 75% of the neurons, you may develop Parkinson's disease and Alzheimer's disease, but most of us do not. But if you live to be 110, probably we could develop to have Parkinson's and Alzheimer's disease. And one of the problems that we are trying to solve in treating Parkinson's and Alzheimer's disease is to develop drugs that prevent this progressive degeneration, either to stop it or in fact try to reverse it. And this is the reason why I'm sure many of you know people taking a lot of antioxidants like green tea, blueberries, wine, you know, vitamin C, etc., to see whether we can prevent the aspect of aging, especially the aging of the brain. So the idea is to be able to identify some biomarkers where we can actually stop this progressive loss of the neurons that occurs in Parkinson's and Alzheimer's disease. So all the drugs that we have today for Parkinson's and Alzheimer's disease are drugs that you treat the disease, you treat the symptom, not the disease. And it's like if you have a toothache, you take an aspirin, it prevents the pain, but you don't solve the problem. You have to go to the periodontist or dentist to solve it. And this is a major problem with Parkinson's and Alzheimer's disease, so we're trying to develop drugs that perverse and restores the neuron. Now, the major problem that we have with neurological diseases, the degenerative neurological diseases, is that once we lose the neurons, we cannot restore them. But lower animals can, and this is one of the main problems. So we have been working, trying to develop drugs that can restore the loss of the neurons. And in my center, we think we have developed a number of drugs which are developing now to restore the neurons, and I tell you what actually happens in. So we have two concepts, neuroprotection. If we knew what causes a disease, we will develop a drug to prevent the neurodegeneration. That's called neuroprotection. You take it, that's why people are taking a lot of antioxidants. By neurorestoration is that we've lost the neuron, and by the time we discover the disease is already too late. The neurons are dying, we don't have a biomarker, we don't know identify who's going to develop Parkinson's disease or Alzheimer's disease. So we're trying to develop drugs which are neurotrophic. They can make the neurons grow again. And to explain this concept of neuroprotection is that most of us don't get Parkinson's and Alzheimer's. We don't fall into the Grand Canyon. But the idea is that if you're going to develop Parkinson's disease, you could have a drug that prevents you from falling into the Grand Canyon, or maybe even if you discover disease later on, you can stop its progression. This is called neuroprotection. You give a drug to prevent it. Now, by neurorestoration, it's different. In neurorestoration, what we are trying to do is to restore the neurons. So I'll start with Parkinson's disease. So Parkinson's disease is the second largest neurodegenerative disease in the world. In the United States, there is maybe 1.2 million people. It's about 0.5% of the population. It would be the same in Israel, it would be the same in China, India, and in Europe. And the disease is normally begins when we see it around the age of 40, 45. James Parkinson discovered the disease in London, on the street of London. He was a famous clinician. He was a Greek classicist, Latin scholar, and he was a very astute person. He saw a man in London, in South Bank of London, that was walking, had masked face, shoulders bending, and he was shuffling, and was a young man. And being type of person, James Parkinson asked him, why was he behaving like that? He said, I have had this malady for some years. There was not a disease, a malady, the name malady, I have had. So he found 4 other people like that, and he published a famous book called the shaking disease, because one of the aspects of Parkinson's disease is shaking. There is rigidity, as you can see. There is the bending of the trunk, rigidity of the arms, and shuffling and the tremor. So this is really the basis of Parkinson's disease. And he wrote himself that maybe this is a disease of the brain. This was in 1817. It was a brilliant, really, and today we still use James Parkinson analysis to identify the staging of the disease. Now, some of the most famous people in the world who have Parkinson's disease are Muhammad Ali and Michael J. Fox. Muhammad Ali has Parkinson's disease. We don't know, maybe from the boxing, of course, the problem. He was hit several times. And Michael J. Fox has a very severe Parkinson's called the juvenile disease. He has what we call complete dyskinesia. He's all the time moving. And one of the problems is trying to develop a drug for this type of Parkinson's disease, which is a very severe disease. And in fact, we are now developing one drug in our company called Abital Pharma, and at the center at the Faculty of Medicine. So what actually happens in Parkinson's disease is that this is a normal brain. And this is the brain area that degenerates. It's called the substantia nigra. And you see this black, it's the black substance. This black substance is called melanin. If you sit in the sun, you get tanned. That's melanin. Now what happens that in this brain area are the neurotransmitter dopamine, which is responsible for movement. And what happens that these melanin-containing neurons selectively degenerate. And you can see in the Parkinsonian, they have become bleached because the neurons have died. And when you look under the microscope on the brain, you see this inclusion body called the Lewy body disease. Now, what is Lewy? It's very important because it was discovered by the Jewish-German scientist called Levy. Levy was working with Alzheimer at the time when Alzheimer, I'll come back to Alzheimer later on, he was working with Alzheimer's disease, and they was examining brains of Alzheimer patients, and they discovered that some Alzheimer patients not only had Alzheimer's disease, but they also had Parkinson's disease. And the pathology of the brain showed these inclusion bodies that Levy discovered, and Levy had to escape from Germany, and he went to America, and he changed his name to Louis, because America gave him citizenship. So he's known as the Lewy body disease. So this is really the basis. The whole idea is to be able to develop drugs to prevent the degeneration of these melanin-containing neurons and maybe even restore them. And what really happens is that the neurotransmitter that is responsible for the Parkinson's disease disappears and is made in this part of the brain, and then is transported by what we call axonal transport to this part of the brain, which initiates the movement and everything associated with dopamine. When these cells die, dopamine disappears from this brain and this part of the brain, and you have Parkinson's disease. This is almost exactly the same phenomena that we see in diabetes. You know, diabetes, the cells that make insulin degenerate, so we give them insulin therapy. In Parkinson's disease, the major breakthrough came about that exactly like insulin replacement therapy, what we do normally to treat the patient is to give them the drugs that restores the dopamine, replaces the dopamine. But we don't really cure the disease. We only treat the symptom and not the disease. So this is really the basis of Parkinson's disease. And if you look at the brain of a normal person, this is the brain area that degenerates normally. This is a 25-year-old person, and this is a 65-year-old person. You can see that already by aging, we have lost these neurons. I hope I don't worry you, but that's what exactly happens. But you need to lose a significant amount before you develop the Parkinson's disease, at least 75% of the neurons. That's so one of the things, that's why people are taking all these antioxidants to prevent from aging, because you want to keep this beautiful organ called the brain. Now, until about 10 years ago, we thought that Parkinson's disease was a purely neurological neurodegenerative disease. But this has now changed in the last 10 years because BRAC in Germany has been following the whole body of Parkinsonian patients, and now we believe the disease is far more complex. It's not a neurological disease, it's a neuropsychiatric disease. And we believe that the disease may actually begin in the colon, because the first time you see the Lewy body, you see Lewy body in the colon. Because Parkinsonian patient, one of the signs of Parkinsonian patient is that they have constipation. This is one of the first things of constipation. Then the disease moves to the heart vagus, because we know that Parkinsonian patients have autonomic problem. Then the disease moves to the olfactory, because Parkinsonian patients lose the sense of smell, and the neurons die in the olfactory. And so the disease is moving, excuse me, from down here into the what we call the brainstem, and two neurotransmitter systems, the serotonergic and noradrenergic neurons are deficient, and so Parkinsonian patients have predisposition to depression before they even develop the Parkinson's disease. So we're getting even more complex. Then the disease moves to the midbrain, and this is where the dopamine neurons degenerate and gives you Parkinsonism. Then the disease moves to the frontal cortex here, this part of the brain, where certain neurons called the cholinergic neurons degenerate, and the person develops dementia. So a Parkinsonian patient has depression, Parkinson's disease, and develops dementia, Alzheimer-like, and is now more complex. And we were naive that at the beginning we were just developing drugs that were only treating the Parkinson's disease and not the depression and what the dementia. So it's really a profoundly complex disease that occurs. Now, even more problem is what happens to the neuron. Numerous investigators from all over the world have been trying to understand what causes Parkinson's. What is the biochemical toxic event that results in the process the neurons die? And nobody knows what's the cause of Parkinson's disease. There may be many ways in which the neurons can die, and many neurochemical toxic, what we call cascade of events, that can result in causing the neurons to die. For example, with the ubiquitin protein system, which processes proteins in the brain, they can become toxic. We know that iron accumulation, I'll talk a little about iron accumulation, then give you what we call reactive oxygen radical. We have usually two very good oxygen and radical oxygen. Radicals can sometimes be very good, but always radicals can cause death, etc. So there is a complex, and what is interesting, we now know that all of these neurodegenerative diseases I have mentioned here have basically the same basis in which the neurons die to give you the various neurodegenerative diseases of Alzheimer, Parkinson. Huntington disease is purely genetic. Now, I must tell you that neither Parkinson's disease or Alzheimer's disease is a genetic disease. Maybe 5 to 10% is what we call familiar. The rest is sporadic. It just starts. We don't know why. We don't know when. We think that Alzheimer's disease may start at least 15 to 20 years before the disease onset, and Parkinson's disease maybe 5 to 10 years. And people are trying to identify early biomarkers that we can intervene at an early stage. And we know from animal experiments that if we had a biomarker which can identify, we can prevent the disease at an earlier stage. Because once you fall into the Grand Canyon, we can't do anything about it. So these are the major problems. So one of the things that we know, we have many animal models of Parkinson's disease. By the way, no animal, no primate, no monkey, no gorilla suffers from Parkinson and Alzheimer's. It's a human disease or the disorder. But we have many models, animal models of the disease, and we can use what we call neurotoxins that we can inject into the brain and kill those neurons, which are called the substantia nigra, the melanin containing, and the animal develops Parkinsonism, but not Parkinson's disease. So this is very important. These are models. And we have many of them. For example, we inject a neurotoxin, 6-hydroxydopamine, and we see exactly like what we see in Parkinson's disease. These are the neurons that die, and you can see the neurons have died, they have disappeared. And what happens in another model, we get this increase of iron accumulating. For some reason, some of you who are chemists, iron plays an important role in producing free radicals, which are toxic, and they can bombard the neurons and cause the neurons to die. This is the model of Alzheimer's disease. This is part of the hippocampus. I'll come back to that later on. That we see that when we use the neurotoxin kainate, it causes accumulation of iron here in the hippocampus, and we know that the hippocampus is important for cognition. So this is part for Alzheimer's disease. So we have a problem with how we're going to solve this problem. So this just to show you what actually happens, what we call with oxygen radicals. We know that in the cells there is an enzyme called monoamine oxidase, AMB, and it produces hydrogen peroxide. Hydrogen peroxide is an inert thing. You put it on your hair and you become beautifully blonde. Okay, it's very nice. But we also know that in Parkinsonian brain and animal models, for some reason, iron accumulates. You know, it's like rusting of a car. When the paint of your car chips, the iron oxidizes, and you see the oxidation of the metal from, we call what, valency to valency, and your car begins to rust. This is really exactly what happens in the brain. The neuron actually rusts because iron causes it to rust and produces this radical, hydroxyl radical, and this hydroxyl radical is really dangerous. So the idea is to develop drugs that can prevent the occurrence of this radical, or to try to scavenge it, to prevent this radical acting on the neuron. I hope you understand. I keep it really simple. So one of the things we have developed is that we've developed drugs that can prevent this enzyme to produce hydrogen peroxide, and we've developed what we call iron scavengers that prevent the formation of this radical, and this is one of the things that I'll tell you that we've developed in the center, at the IFTOP Center, and in our company, and we are really developing this for the treatment of Parkinson's disease and Alzheimer's disease. And really, this is the molecule of this beautiful dopamine, because dopamine is the crux of Parkinson's disease. What we do, all the drugs that we have, we give drugs that can increase the level of this neurotransmitter dopamine in the brain to prevent the symptoms of Parkinson's disease. But this drug, the dopamine does not really change the course of the disease, and the disease continues to progress, and of course it takes 10 to 15 years before the patient dies. So one of the things we know that this dopamine is synthesized in the brain from an amino acid called tyrosine, and then dopamine is released in what we call to the neurons, and they have receptors. These are called D1 and D2 receptors, and these receptors, once they see the dopamine, they are initiating movement. They cause the neurotransmission in the brain, and you can move. And of course, if you don't have dopamine, these receptors are not stimulated, so you have the problem of akinesia, the patient cannot move, etc. Also, one of the major problems with Parkinson's disease, exactly like what happened with insulin therapy. When insulin was discovered, they said, oh, we have discovered the cause of diabetes, we give insulin, everybody can go home, etc. But long-term treatment with insulin produced so many other side effects, complications, cardiovascular problems, etc. The same thing happened when the dopamine therapy, L-DOPA therapy, discovered. After 3 years of treating patients with L-DOPA, the patient improved. About 3 years after L-DOPA, the patient developed a terrible symptom that they take their L-DOPA, they move, and then they suddenly freeze. They cannot move anymore. And then maybe 5-10 minutes later, they start moving. This is called the on-off, on-off. And sometimes it can become so bad, it's known as a yo-yo effect. They can move and they stop, they move and they stop. And this is one of the major side effects of long-term treatment with L-DOPA. So we have a lot of problems that we have not solved. So one of the things we've done, we developed, in 1975, I developed this drug selegiline. And here, Professor Moshe mentioned that we developed a very successful drug called Azilect, which is now considered the major drug for the treatment of Parkinson's. I think it's now the major drug for the Parkinson's disease. And there is a suggestion that this drug may be the first disease-modifying drug in the world for Parkinson's disease. There is a controversy, some people say yes, some people say no, but it's a very important drug. It's a very easy drug. You take 1 milligram, 1/1000th of gram every day, and that is a very active compound. And then we developed a new drug for Alzheimer's disease called ladostigil. I'll come back to that, in which we developed it from Azilect with Teva, and it's now in our company. But the ones that I want to talk about are these drugs that we developed in our center at the IFTOP Center. These are the iron scavengers, which I mentioned to you. We want a drug that prevents the iron producing those radicals, And I'll be talking for this very important drug, which is an iron chelator, or the iron scavenger, as well as preventing, inhibiting, or inactivating the enzyme monoamine oxidase that produces hydrogen peroxide. So it's a multi-target, what we call multi-target drug. I just came back actually from a meeting in Florence and Siena on multi-target drugs for neurodegenerative diseases, which is now a major aspect of the disease. And what is interesting with this drug, when you give it to animals, it increases the brain level of dopamine, which we know is important for Parkinson's disease, and it increases these neurotransmitters, serotonin and noradrenaline, and these are two neurotransmitters which are important for the aspect of depressive illness. All the drugs that we have for the treatment of depression per se, are drugs that act on these two neurotransmitters, and drugs that can on dopamine are drugs that act for Parkinson's. So we have a drug which is multifunctional, is both antidepressant as well as anti-Parkinson. And this is the concept of multi-target drug that came from my laboratory, and at the conference in Florence, everybody is now trying to develop these multi-target drugs similar to the ones that we've developed. And one of the drugs that we have, we're hoping to, at the end of this year, to get an IND from FDA to start a clinical. Now, what is so important about these drugs? This was discovered from one of my really brilliant students, Yael Abramovich, that when he took these cells, these are called neuroblastoma cells, and they look like this. And she took these new drugs and she put them into cell culture in the incubator and found that they form neurons in the cell culture. That means these drugs had trophic activity. There was something about these drugs that converted these drugs to neurons. And this GAP43 is an indicator of neuronal formation. There are other markers, but this is one of the most famous. So it seemed that this drug had something very special. I said, oh, maybe this drug really has something which nobody else has, that it has ability to cause the neurons to regenerate. So I'll show you some of the experiments we did to show that indeed this drug has a unique, we think it's really profound, is what we call our blockbuster in our department, is going to be our blockbuster. Now this is an animal model of Parkinson's disease. This is in mice. We take a neurotoxin called lactocystin, and this, by the way, this is the brain area in the mice that degenerate to cause Parkinsonism. So we use a number of animals, rats, cats, mice, monkeys, of course we use, but unfortunately we cannot use monkeys now in Israel because we have a problem. El Al does not transfer monkeys anymore. But many of the airlines have stopped transferring monkeys to Israel because of the animal rights people. We have a lot of problem. But we use mice. What we do, we take this toxin and we inject it into the brain, in the brain area which contains the dopamine neurons that gives rise to Parkinson's disease. You see, after 7 days, some of the neurons have died. After 24 days, all the neurons have died, and we know that the dopamine disappears from this brain. And the animal, as we call Parkinsonism, cannot move, etc. But if we take our iron scavengers or iron chelators and inject it before we give lactocystin, it completely protects. This is neuroprotection. I mentioned to you that we don't have a biomarker for Parkinson's disease. We don't know who is going to develop and when develop. By the time we discover the disease, it's already too late. We are falling into the Grand Canyon. As simple as that. But this is really the exciting one. We give the neurotoxin and we cause degeneration, and then we start giving our drugs after we have caused, and you can see the neurons come back. This is neurorestoration. We know of no drug being developed by any other group or pharmaceutical company that has this neurorestorative activity. And we, in fact, I won't go into detail. We know exactly how it does it because we discovered that this drug releases certain hormones from the brain that what we call neurotrophic. That means if you put a plant in front of the window, it goes towards the sun. And we think these drugs definitely have neurotrophin activity. We know exactly it releases 4 neurotrophin that can make these neurons grow. And many people, we have sent the drug to many laboratories, including to Weizmann Institute, and they have confirmed it, that these are unique drugs that not only have neuroprotective activity, but they also have neurorestorative activity. And they really act to prevent the accumulation of iron that you see. It prevents the accumulation. So for some reason, we don't understand how this iron that accumulates can cause the degeneration of the neurons. This is just, actually, we haven't published this. We just got this new result. This is another way of looking at another model called MPTP, which is a very interesting neurotoxin. In 1979, a medical student at Georgetown University was a drug addict. He was addicted to an opiate called meperidine, which is an anesthetic used in surgery. It's like, not cocaine, it's an opiate. And he wanted to get more of it, he couldn't, so he set up a drug designer's laboratory in the basement of his mother's house. He went to the National Library of NIH, got the method how to make meperidine. He started synthesizing it, he injected him, and 3 days later, he became completely Parkinsonism. He was a 21-year-old medical student. Nobody knew what was happening. The police of Washington, and they brought him to the hospital. They didn't know how could it be. There's never been a person with Parkinson's disease at the age of 21. It was unique. One case can completely revolutionize medicine. So the police of Washington zoomed down to the mother's house. There was a drug discovery, the drug laboratory there. They find the crystals, they bring it to the National Institute of Health, they analyze it, and they discovered it contains a compound called MPTP, which you could buy grams of it for a few dollars, and the Americans were going to use it as a defoliage in Vietnam because it's like paraquat. Paraquat is used on the farming industry in Israel to weed the fields or all over the world to get rid of this so that they can plant. Anyway, what is happening, later on they discovered that if you give this MPTP to monkeys, to mice, and to rats, it causes the degeneration of the melanin-containing neurons, and the animal becomes Parkinson. This was one of the most important models to be discovered for Parkinson's disease, and we have used it, and you can see this is the normal animal, this is the degenerate animal, and when we give our drug M30, it completely restores the neurons. So we have used a second animal model. So we are very excited that this drug really has something special about it, and of course we are in the process of developing it. So how does these neurons really regenerate? We know that the hippocampus is an important area of the brain for cognition. And everybody's doing exercise. Anybody here doing exercise every day? And do you know why? No, it's not a joke. Because my colleague, Michael Sigmund at Pittsburgh University, has developed this animal model that when he puts the animals in treadmill, he causes them to become Parkinsonism with this drug, and he puts them in the treadmill, and the neurons come back. This is not a joke. This is why exercise, both intellectual exercise and physical exercise, is considered to be important for the treatment of dementia and Alzheimer's. Everybody's running around, etc. I do at least 10,000 steps a day, by the way. And so this is the hippocampus. We know that in this part of the brain, you can get what we call neurogenesis. Neurons can grow. And we think what's happening that our drug is causing these neurons to migrate from the hippocampus down to the brain area that degenerates, and we think this is one of the really exciting things. And of course, neurogenesis and making more neurons is important because as you become older, become more demented, and forgetful. But of course, Alzheimer's disease is different from pure dementia. I'll show you what happens. So now, what about Alzheimer's disease? Is even more complex because we know in Parkinson's disease a special nuclei in the brain degenerates. But Alzheimer's is a far, far more complex disease. First of all, even if you develop an animal model of Alzheimer's, You cannot talk to him. You cannot know what he's learned. But in the model of Parkinson, is a movement disorder. And so we have to devise new method of trying to understand Alzheimer's disease. And this was the first patient that Alzheimer showed had Alzheimer's disease, and of course the patient died, and the brain was examined, and I'll tell you what happens in the brains of the Alzheimer patient. And of course, it is probably the most devastating disease of the 21st century. Right now, between 4 to 8 million people in America have dementia, Alzheimer's disease. It's considered by year 2020, the cost of just looking after Alzheimer's disease in the United States will be equivalent to the cost of the American Defense Forces. They're going to talk about $400 billion a year, because Alzheimer's disease is a much more complex disease, because the patient forgets. You have to have at least 2 nurses to watch out, because the Alzheimer's patient can go out at night, they become psychotic, they open the door and they go out and they cannot find themselves coming back. You know, this is far more, and we don't know what to do about it. And so there's tremendous the group of people all over the world trying to understand it, and of course the prevention is important, and we really didn't know much about it until 15 years ago. It was first described, the pathology was first described at the Neurological Institute in London, in England. And these are some of the most famous people, some of the famous people who had, this is Alzheimer. This was his first patient, of course, Charlton Heston and President Reagan. And look what happens in the brain. This is a normal brain. And this is a brain atrophies, it shrinks the brain. And these gaps begin to occur, and you can see the comparison between the normal and the Alzheimer brain. Vacuolation occurs in the brain. And when you look under the microscope, you see these tangles, these plaques. You have heard of the CNR plaques. I'll come back to this because this is a certain protein. These protein aggregates, and they form plaques in the brain over the neurons, and they cause the neurons to degenerate and stop functioning. That's one problem. And then you get this wire-like, called these wires, tangles. These are tangles, those are plaques, okay? So we get in 2 types. And there is actually a fight between the people, at least the scientists, people who think that the plaques are the one that causing Alzheimer's disease, and people who think tangles. And we think this is not true. I think both the plaques and tangles contribute to the Alzheimer's disease. And of course, if you have Alzheimer's disease, you cannot play chess, because you don't know what the movements are. So this really shows you the prevalence, of course. And one thing about Parkinson's disease, Alzheimer's disease, that the incidence increases with aging. This is the whole problem of aging. I see that most of us do not become, of course, Alzheimer or Parkinson. And so the progression is one of the major indicator of the development of the disease, and there is a significant financial burden, of course. And the drugs that we have for Alzheimer's disease today are not as good as for those of Parkinson's disease. And this gives you the incidence of the disease increasing with time, and of course, every year, I think every 10 years it doubles. And so this is the complex neuron that we see in the brain. And I'll show you what actually happens, how the progression of the disease occurs in Alzheimer's disease, which is, as I said, far more complex. These are the normal neurons that we see in the brain. And then we get, of course, this neurotransmitter, acetylcholine, which is considered to be released at the site of the receptors for this neurotransmitter that initiates cognition. I believe is far more complex than just one neurotransmitter. And what really happens, these are the plaques I mentioned to you that form on top of the neuron. These protein aggregates, these proteins are called beta amyloid. It's a large protein. We don't know what their function is in the brain, but they aggregate, they sit on top of the neurons and prevent the neurons from. So just to give you a little biochemical analysis, is that the plaques are formed from the deposition of proteins called amyloid. And this amyloid, we believe that the original amyloid is a good protein, but for some reason it's converted to what we call to the beta amyloid deposition, and they form the plaques here. And of course, they act on the synapse in the neuron and neurotransmitter disturbance and Alzheimer. And the other one is the tau, the tangles I mentioned, these wire-like things that you actually see in the brain of the Alzheimer. And they also cause changes in the synapse, neurotransmitter synapse, neurodisturbance, and Alzheimer. So we have two processes that occur. And of course, I mentioned there is a controversy fight between the people who believe in the plaques and people who believe in the tangles. We, in our center, believe that they're both involved, and we have to develop drugs that would prevent the formation of the plaques and these tangle wire-like tangles. So multi-target drugs become an important issue for them. And so this really, I want to show you, but this is really part of the brain compared with the control and Alzheimer. And these really are the tangles. So what happens is that the disease really begins to start here and slowly spreads across the brain. As you can see, this is a diagrammatic person, and this is the why that you have this atrophy of the brain. The brain as a whole is completely, the atrophies, it shrinks and gives you this. In the same way that I mentioned to you in Parkinson's disease, we see the same thing happening in Alzheimer's disease, this accumulation of iron. We don't understand where this iron is coming from. I've been working on this iron metabolism for 30 years. I still don't know how and why iron accumulates. And the question is, I'm sure your grandmother, your father said your brain is rusting. It's really true. With aging, for some reason, iron accumulates in the brain and the rusting brain. I've published a number of papers on this. And we know that if we can prevent this iron accumulation, it can be an important aspect for the treatment of Parkinson's disease and Alzheimer's disease that results in a whole battery of biochemical events that results in the collapse of the neuron. Now, I mentioned to you why people are obsessed with all of these nutrients like oranges and lemon teas and colored fruit, because these nutrients contain certain substances called polyamines. And these polyamines are both radical scavengers as well as ion scavengers. And Moshe mentioned that I have an appointment in Hong Kong and in China, because we discovered Chinese green tea is really a potent, it has a component called EGCG. We isolated this EGCG from the Chinese green tea, and it has a potent ion scavenging and radical, and we showed it that in animal models that it had anti-Parkinson, anti-Alzheimer activity in animal models of these disorders. And a study in China just recently came from Beijing that in a control study, this EGCG, this component of green tea, does have anti-Parkinson effects. So people have become really obsessed by taking certain foods, certain nutrients, especially in Europe and America, that can prevent the whole process of aging. That's the green tea. So oranges, salmon, that's why it's important, because it has important constituents. Chocolate is important. These all got polyamines, especially blueberries. I once gave a talk at the American Technical Society in Los Angeles, and I told them about blueberries, and they were serving blueberries. By the time I came out, all the blueberries had disappeared. Really, it's not a joke. So a blueberry is a big component, and I get invited by the Blueberry Board of America. Every year they have a conference on it to talk about my green tea component, because they contain this polyphenol, very important polyphenol, which is a radical scavenger, as well as ion chelator. Now, if that doesn't work, I think you should become a conductor. And it's very interesting, very few conductors become demented, because first of all, they do both exercise as well as mental exercise. So I put this picture up, it's a very interesting thing. So I always say, maybe you should become a conductor. So in the current, we have a major problem with Alzheimer's disease. There are only about 4 drugs that are available for Alzheimer's disease, and these are drugs that increase the neurotransmitter acetylcholine, in the brain. At best, maybe they're effective maybe in 14 to 25% of the patients. We have a major problem with Alzheimer's. It's far more complex because it really, as I show you how the disease moves across the brain. And one of the most important is this drug is called Aricept, the donepezil, developed by Eisai company in Japan. There is one developed in Israel called Rivastigmine, developed by my colleague Martha Weinstein at Hebrew University. That these are all basically mild, at best mild treatment of Alzheimer's disease. And what people are trying to do, I mentioned that this is really a complex pathology, and they're trying to develop drugs at any one of these sites, like anti-inflammatory. We know that there is an inflammation in the brain. We know there is oxidative stress formation, the generation of radicals. They believe there may be toxins that accumulate in the brain. So as a whole in the world, people are trying to develop different drugs for different sites. But since it's a multifactorial disease, we think that the drug should be multifunctional, that can act on different sites in the brain at different components. I mentioned to you A-beta because this is where most of the research in the pharmaceutical industry has been. In the last 2 years, 4 drugs have failed because they were developing drugs to prevent the formation of this beta amyloid that I mentioned to you. So we are really nowhere near trying to solve the problem of Alzheimer's disease or to have a better therapeutic as we have for Parkinson's disease. We can manage Parkinson's disease because we have many important drugs. So I mentioned to you that both Parkinson's disease and Alzheimer's disease are neuropsychiatric diseases. 40% of Alzheimer's patients have what we call Lewy body disease. Lewy body disease are the ones who have both Parkinson's disease as well as Alzheimer's. And Alzheimer's patients, like Parkinson's patient, also have predisposition to depression. So we have the neurotransmitter dopamine, which is important for Parkinson, acetylcholine, which is important for dementia, and the neurotransmitter serotonin, noradrenaline are for depression. So we decided to develop a new drug that will have all of this activity in one drug. So what we did, we took our drug, anti-Parkinson Azilect, known as Rasagiline. We took the anti-Alzheimer's drug Rivastigmine that Martha Weinstock had developed at Hebrew University. This is marketed as Exelon by Novartis. This is marketed by Teva. And we took this part of the molecule, which is important for the cholinergic neurotransmission, and we stuck it into Rasagiline. We made a new compound. And this drug is called Ladostigil. Now, you have to believe me, I can't go into detail. This drug has anti-Parkinson activity of Rasagiline. It has the anti-Alzheimer activity of Rivastigmine. And one of the most fascinating about pharmacology is serendipity. When you make a drug, you don't know what it's going to do. And we discovered that this drug also had antidepressant activity. So Ladostigil now is an anti-Alzheimer drug. We now have, this drug is now in what we call phase 2b studies in 19 centers in Europe. We have a company called Abram Pharmaceutical, which I didn't mention, and we're hoping in 2016 to get the results. This is a double-blind study of 250 they're not Alzheimer's patients. What we call, these are the patients who have mild cognitive impairment, and they become Alzheimer's eventually. So we are giving this drug to see it can prevent them becoming Alzheimer's. So that's why we have to do a long-term study to see whether this drug prevents their conversion to Alzheimer's disease. And so, mentioned to you that Ladostigil has anti-Alzheimer activity. It has anti-Parkinson activity, and it has antidepressant activity, and this is one of the discovered after we made the drug. We didn't know that it would become. I can't go too much into detail of this because we know that inhibitors of monoamine oxidase A, not the B, are antidepressants. So we discovered that this drug had this activity, and so this is why this is a unique and very exciting drug development. We hope that it will be successful. As I mentioned to you, that already 4 major drugs have failed by the big pharmaceutical companies in Europe and United States. So how do we actually develop a drug for Alzheimer's disease when you cannot talk to the animal? So what we do, there is a very interesting model called the Morris water maze. This is a tank of about 1.5 meters in diameter and about 1 meter deep. It's gray, and you fill it up with water. I hope this works. And it has a platform. It has a platform there. And then you pour the water that just covers the platform, and then you put milk powder over the water so that the rat and the mice cannot see it. And then you can put the mice or the rat anywhere in this tank, and the animal has to find the platform. Okay? Now, it's a gray tank, so he's not using the gray surface of the tank. He has to use the cues of the room. He sees me, he sees the camera, he sees the window, and believe me, if you put a rat or a normal rat or mice, with 8 to 12 tries, they'll find a platform, and each time you put it, they go straight into the platform because they don't like to be in the water. They learn. Now, we can give a drug called scopolamine that prevents the action of the neurotransmitter acetylcholine, and when you give this to the animal cannot find the platform. So here it is. This is the drug scopolamine. Okay, you give it to the animal. This is the normal animal. After 4 days, he can find the platform quite easily, nicely. You give him this drug scopolamine, and the animal, no matter what, cannot find the platform. So what we did, we took our drug latostigil at 2 different doses, and we gave it, and you can see that our drug prevented the scopolamine action, and the animal could find the platform. This is the way the industry uses this Morris water maze. There are, in fact, in our laboratory, in our center, we have used about 8 different behavioral learning parameters, famous, etc. And I'll show you 1 or 2 of them. So this is the scopolamine method. So, and this is a rapid pharmacological way that the drug really has ability to prevent the action of scopolamine after you've given scopolamine to the animal. And really, this is basically what the tank looks like. Now, the other way to do things is we have now what we call transgenic models of Alzheimer's disease that can produce what we call, remember the beta amyloid and plaques, there are genetic models, the transgenic models in which these animals have an incredible amount of plaques in their brain, and they cannot learn to find in the Morris water maze. And you can see this is a double transgenic mice called the APP Swedish mutation and priscillin. 2 genes are altered, and these animals have tons of plaques in their brain, and they cannot find a platform. Now, we give our new drug, this multi-target drug M30, which I mentioned, which was for Parkinson's disease, I remember, and I told you also it had causes, and it has antidepressant. Now we examine it, and you can see that when given at extremely low concentration, 1 milligram and 5 milligram orally, because if you're going to develop a drug for clinic, it has to be oral. You cannot, injection is not, it's okay in the laboratory, but orally for about 3 months, and we see these animals really learn, they were able to find a platform identical to controlled animals, the wild animals which were not transgenic. So we are very excited about this. So M30 now has this cognitive enhancing activity. So I mentioned you M30 had anti-Parkinson, antidepressant, and it increased the brain neurotransmitters, which are important for these conditions. And now we see that it has this cognitive enhancing activity. The other thing is that, of course, we know Alzheimer's patients cannot care for themselves. And these double-transgenic mice, if you take a mice and put them in a cotton wool, they make a nest. It's called the nest making. We have actually videos of this. I didn't bring the video. But if you take the double-transgenic mice, which I showed you from the previous, and you put them in the cotton wool, they cannot make the nest, but when we treat them with the drug M30, they make the nest. So this was another test that we used. As I said, we have 7 different kinds of tests, and also the raw value was published really in the top journals a year ago. And this gives you a better view of what I'm talking about, these double-transgenic mice. You see the plaques, thiophyllin plaques, and when we treat them with the drug, our drug, the plaques disappear. These are in the hippocampus, 3 brain areas, the frontal cortex, the hippocampal area, and the parietal cortex. So you can see slowly the plaques disappeared, so we are very excited about the ability of this drug to do what we've done. And also, not only the plaques, but also the beta amyloid, which form the plaques, are almost disappear slowly with treatment at 2 doses, oral doses. So we are very excited about this new drug for Parkinson and Alzheimer. And as I mentioned, that there is a homology between these neurodegenerative diseases of Parkinson and Alzheimer. At one time, we thought that Parkinson's disease was only a movement disorder, and we thought Alzheimer's disease was only a dementia. But they show overlap, that they can develop Parkinsonism, they can develop depression, and it's a thing. And some people believe that actually these diseases are like a domino effect, because the neurotransmitter system in the brain do not work in isolation. When one of them falls, the other one begins to fall. And we coined up the concept of domino effect. If you put 10 dominoes up, you press one, all of them fall down. You press the middle one, they all fall down. So this is, we believe this is what's happening in the brains of Parkinson and Alzheimer. That's why they show this homology of having a whole variety of CNS problems, because the systems begins to fall, weakens the other. So in my conclusion, it's a philosophical actually. Why is it that we do not see Parkinson or dementia even in the highest form of the primate? I believe that our brain is far, far more complex than those of even the highest primate. And I always bring to my students the concept of Jaguar, fantastic car, brilliant, and Volkswagen Beetle. You can drive a Volkswagen Beetle for years, it almost never breaks down, because it's a simple car. But when I have a Jaguar with this sophisticated machine, anything can go wrong. And I believe this is exactly what's happening in our brain. We have a far, far more complex neuronal system which have to be tuned to be, whereas in animal models that we use are less viable, because I think they're simpler, even though we have roughly about 78 or 80% of the animals have the genes that we have. So this is, I think, one of the things that the problem we have, because we really don't understand all the aspects of this beautiful organ, the brain. So our concept is that we were naive 30 or 40 years ago when we said we developed one drug for Parkinson and it's going to act on one site or one for Alzheimer's disease. We think now the concept is extremely viable, because these are multifactorial. And we learned this from actually what was happening in the treatment of cancer and AIDS, especially AIDS. I don't know whether any of you have followed the aspect of what happened with AIDS. When they developed one drug, they couldn't treat the AIDS. And there was a famous film recently, The Dallas Boy, the guy that won the Oscar portraying this AIDS person. He was given 3 months to live and gave him one drug. No, he decided he was going to Mexico, to England, to Amsterdam, and he brought all sorts of drugs, and he treated himself with polypharmacology. He lived to be 7 years. And this was one of the major breakthroughs in AIDS, because people began to say, no, we cannot use one. We have to use a number of drugs to prevent this devastating disease. And now today's treatment is polypharmacology for AIDS, polypharmacology for cancer. Now, the new concept for neurodegenerative diseases is also polypharmacology. So we have a drug that has anti-Parkinson, and it was designed to have antidepressant. We know that it has this iron scavenging, prevents the formation of radical. We now know that it prevents the cognitive aspect of the glutamate area or kainate, which causes the hippocampal degeneration. It prevents it. We also mentioned that it really affects the beta amyloid, which are important. So we think this is really the future, and the conference I just came back from Florence was an international meeting. The new concept for the treatment of these complex neurological diseases is the use of multi-target drugs. We hope that it will be successful. And this really shows you my group. I only have girls, or they used to have only girls in they were wonderful. I want to especially mention Yael Abramovich, who really discovered, I showed you the slide in which he showed this differentiation of the cells to neurons. Sunit was the one who discovered that these drugs have neurorestorative activity. Taman and Oli have done all the behavioral aspects in their Alzheimer model. And Henry is a psychiatrist, a biological psychiatrist who does works with us on the behavioral aspects of the disease. And Sylvia Mandel, who has now left us, worked on some of the genetic aspect of the Parkinson's disease, which I did not talk about. And thank you very much.